This is a level 1 diagnostic on why copying stuff from memory is not always the same as copying stuff from memory. It's like, what's the context of this project? What's the context of this level 1 diagnostic? What isn't working correctly? Well, we've got the Looking Glass project, which copies the frame buffer from a graphics card into host memory, into shared memory, so that you can see what's going on a virtualized graphics card on the host operating system. That means you can run Windows games under Windows, under Linux, at full speed, or we're getting there. The faster we can copy stuff off the guest graphics card, the better experience you're gonna have playing that game under Linux, under Windows, under Linux. It's kind of cheating, I know. So you would think, I mean, half of what a computer does is copy stuff from one place in memory to another place in memory, or copy stuff from a device to memory. That's one of the first optimizations the computer got, DMA, direct memory access. The CPU says to a peripheral, hey, guy, write to this place in memory, here's your pointers, here's your buffer, here's whatever. That 32 megabytes or that 8 megabytes or whatever is all yours, and you just do it. It's literally half of what a computer does is just copy stuff to memory. So we ran into a problem with Looking Glass where memory copies on like a Threadripper quad channel system, 0.7 milliseconds. That's pretty good. That's almost the memory bandwidth. Well, it's not quite the memory bandwidth, but it's really fast. I mean, that's over 32 gigabytes a second from our code, from code that we wrote that's not really super optimized. And then on an Intel i9 system, it was more like 1.5, 1.6, 1.7 milliseconds. Huh, that's weird. I mean, that's still really fast. If you're doing a 32 megabyte 4K frame buffer and the system's not doing anything else, it's over 1,000 FPS. But in practice, it's not really so cut and dry. It's not really so simple. So the diagnostic here was to figure out why memory speeds vary so wildly. I mean, we could run A/64 and see the memory bandwidth. We can also see the latency. Maybe this is latency related. And we've got to do a deep dive and go into all of that stuff. So I've been working on this video for a while. I've been trying to figure out how to present it in the least boring way possible. But there's just no way around it. I'm gonna have to get a little bit rambly so that you understand the parameters of the project. But this will serve you well in the future. If you need to do this type of diagnostic on your own code or for your employer or for your own side projects, this will help you to understand what's going on. Too many developers, myself included, are like, this is bear country. I don't really want to dive into this. The compiler should figure this out for me. But in this case, I feel like the compiler has missed the mark. Let me explain why. So you use GCC, and you compile a little memory tester program for 32-bit systems, and all of a sudden 0.7 milliseconds on a Threadripper system goes to 3.3 milliseconds. That's a lot worse. Why is that a lot worse? How do you investigate that? I mean, it's just GCC. We're literally just talking about memcpy, M-E-M-C-P-Y. It's a routine in C++ programs to just copy memory. So why is 32-bit versus 64-bit so much slower? If you look at the GCC man page, GCC supports a lot of different microarchitectures, and my assumption, which it turns out is incorrect, would be that the compiler, it's really hard to outsmart the compiler, especially with something as fundamental and low level as memcpy. Memcpy should be in like every program under the sun, and memcpy should always be optimized no matter what sort of a condition you're running in. The Intel 386 is from forever ago, over 30 years ago, and it had its own way of copying memory. But then, memcopies is so common that every CPU generation since then has added more and more stuff to deal with memory copies. And now we can do memory copies with like AVX 512, and that's insanely fast. And so that's a family of assembler instructions. It's like a single instruction, multiple data, SIMD. And I'm really glossing over a lot of detail, a lot of computer architecture detail, a lot of computer science. But this is not a problem that you can solve without really understanding what's happening under the hood. And even when you understand what's happening under the hood, you have to do a lot of digging to figure it out. So back to our problem. GCC with the identical program, identical compile options, literally just saying target this microarchitecture and copy this, and it doesn't work. So we can target Opteron because we're doing testing on a Threadripper system. Intel is faster, but we'll get to that more in a minute. And so with the Threadripper system, 3.3 milliseconds just compiling for 32-bit, but 64-bit is 0.7 milliseconds. Why is the speed difference there? That's crazy. That's a crazy speed difference. Well, a 64-bit program can copy 64 bits at a time, and a 32-bit program can copy 32 bits at a time, but it's more than twice as slow, so it's almost 4 times as slow. Well, actually, it's over 4 times slower. That doesn't make any sense. But not only that, there are other instructions for copying stuff in memory that are available in 32-bit space. Like, you can't use a 64-bit instruction in a 32-bit program, asterisk, footnote. But there are other instructions like SSC2, SSC3. There were things to accelerate copying from memory faster than just 32-bit instructions. So discovered, suspected GCC might be doing something weird there, or things are not working really well. The thing that threw us off the scent, so with GCC you can use -S and look at an assembler dump. I know a little bit of Intel assembler. And so you look at the assembler dump and you just look at it and it's like, okay, the 32-bit program is using 32-bit registers, the 64-bit program is using 64-bit registers. I guess GCC probably would have optimized a memory copy, but maybe memory copy is so common that it just happens at the at the microcode level, or the CPU deals with it. It's like, oh, this is a memory copy operation. I got this, fam, and it just handles it. And so if you look on like the Linux kernel mailing list about memory copy and making memory copy faster, there are all kinds of threads. There's all kinds of really interesting stuff about memory copy and making memory copy faster, and all this stuff that goes into memory copy. And the consensus there is generally you can't outdo the compiler. The compiler's good. But looking at that assembler source, it really didn't look like anything special was going on. So on the Intel system, run the 32-bit program, it actually performs decently. Not great, but better than Threadripper. So it seems like Intel has microcode optimizations so that when Intel sees all of this sequence of instructions that looks like a memory copy, it quietly replaces it with something that's not horribly inefficient. Threadripper has that apparently for 64-bit memory copy operations, but it does not have that for 32-bit memory operations. Or maybe not, I don't know, that's a guess. So how do you troubleshoot that? How do you go from there? Well, we did the assembler dump, and 32 to 64-bit, the programs do basically look identical, but let's have GCC target different microarchitectures, because I know that there are extensions that are available in 32-bit instructions like SSC2, SSC3, that should be available on a 32-bit binary. And no matter what I do, no matter what, if I tell GCC to unroll loops, if I tell it to, third level optimization, second level optimization, there's all these options to the compiler. It just doesn't seem like it's really trying to optimize memory copy. Open up a debugger. Let's step into memory copy, because memory copy is a routine that is provided by the library, and sort of figure out what's happening. And when you do that, you can see that memory copy is doing things like looking at CPU ID, looking at what instructions are available, and doing all this really fancy, complicated stuff to try to figure out what is available for copying memory the fastest way possible. Because remember, every CPU generation since the i386 has provided more and more stuff for copying memory in faster and different ways and in different scenarios since the beginning of time. So with compiling in 32-bit, it seems like, oh, you're 32-bit, just don't even bother. That seems lazy of GCC. All right, let's abandon GCC, let's try Clang. So with Clang, it had pretty much identical behavior. I don't want to gloss over it a little bit, but this video is already running a little long. Clang does pretty much the same thing. The performance with Clang was still about 3 milliseconds, even with optimizations on a 32-bit compile. 64-bit compile, 0.7 milliseconds, again on our Threadripper system. So with GCC down and Clang down and not really getting anywhere, not really getting any traction, it's like, okay, is the solution here really to just, roll our own and DIY a memory copy? You should not be, as a developer, you should not be doing low-level things like that. The computer should be doing that for you. It should not force you to think about that. It should just work. There should be a way to do that. And there is a memory manager that is available in, there's actually several memory managers available in C that are trying, because you don't want to manage your own memory. And so when you allocate memory with malloc, that's just, it's a whole, this is like staring into the abyss, and it's so complicated that sometimes the abyss stares back. So anyway, how do we make Looking Glass faster? How do we take advantage? We know the instructions are available, SSC2, SSC3, whatever. We implement our own memory copy, and our memory copy is not faster. In fact, it's probably slower on 64-bit systems when the compiler actually does its job and optimizes memory copy, we're not gonna beat it. In fact, we're gonna make it worse. We're gonna make it substantially worse. But when we're on a 64-bit system and we're compiling with 32-bit, our setup is much better. And we can verify that because, hey, guess what? When we're using SSE2 registers, yeah, SSE2 that came out in what, like 10 years ago? When we're manually using SSE2 registers to copy 128 bits at a time, 8 instructions in parallel, as a matter of fact, that's how I've set up the C program, then all of a sudden we're back down to our 0.7 to 0.8 milliseconds to copy those, whether it's a 32 or 64-bit system. We'll circle back. We do GCC-S so we can see our source code again. I'm looking at the source code in a file comparison tool that's usually used for diffs. It's called MELD. MELD is awesome. You should check out MELD. But I can see that the 32-bit program and the 64-bit program the source code is basically identical. So yeah, that's nice. So we're using the 128-bit registers in either scenario. And so there you go. What's happening is the compiler is taking the built-in memcpy routine that's available in the library, the standard system library, and inlining that into the code. Now, fortunately, we discovered later that there is actually an option to GCC to tell it not to inline anything, and then it'll use the system's memory copy routine, which theoretically will do the CPU ID checks and say, oh, SSE2 is available, oh, SSE3 is available, and copy the memory that way. But it did not seem to work consistently across multiple different machines. So I put together just a little rock dumb stupid SSE3 copy routine that always uses SSE3 registers, and the compiler can't break it or do anything bad or dumb. And I put that on GitHub, and so we could test it on a couple of different systems because these systems are scattered all around the globe. And sure enough, everything is fine. 32-bit, 64-bit, the performance is really super consistent. The annoying thing is that SSE2 was added as an update to MMX in like 2004. Now I'm using SSE3 here, which was added with the Core 2 Duo, but it's still available to binaries that are compiled in 32-bit. That's not always the case. It's like, I want to use AVX 512 with my 32-bit binary. I don't think that's gonna work for you, Chuckles. So, you know, they just assume everybody's gonna have to go for 64-bit. And why the difference between 32 and 64-bit? Well, it has to do with some constraints, operating system constraints, and other stuff that we're running up against, because remember, the other half of Looking Glass is a binary that runs on Windows. So, and games are 32-bit sometimes. And so it turns into a rat's nest of crazy. Don't worry about that part of the diagnostic. So based on this information, Jeff was like, yeah, you know, let's just do this in assembler. And so he did a bunch of inline assembler to sort of do this copy routine. And now using Looking Glass, even from VM to VM. So like if you have a Windows VM and a Linux host and then another VM, you can copy all of that stuff from the guest to the host, back to the guest, basically with no performance penalty or a very low performance penalty, which might be useful in the future. Well, it's useful in a lot of different scenarios, and it's useful in the context of things like Cubes OS, where maybe eventually, although philosophically the Cubes OS people are right not to support this kind of stuff because the low-level hardware itself is not designed with security or hardening in mind. So that can be another level 1 diagnostic for another day. So hopefully I haven't rambled too much. Hopefully you found this interesting. I would like to do more content like this, but I would also like for it to be shared and monetized, and you know, so like it or don't like it if you didn't like this kind of content, and hit the subscribe and you know, all that, comment. Join the forums and actually help us work on these kind of projects. You know, the GNOME Foundation just got $1 million to help them do some really cool stuff. Maybe they're gonna get some performance optimizations and stuff in GNOME, because there's stuff in GNOME where it's like, this should be in a different thread, or I click my CPU frequency button and then there's like a 1-second delay and then it comes in. What's going on with that? So maybe we can fix some stuff like that too, but we need the tools to do a deep dive to understand exactly how this stuff is failing in order to understand how to fix it.